18th International Physics Olympiad 1987 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Write me if interested. My email is fred1996@hotmail.com. Problem 1. Ascending moist air. Moist air is streaming adiabatically across a mountain range as indicated in the figure. Equal atmospheric pressures of 100 kilopascals are measured at meteorological stations M0 and M3 and a pressure of 70 kilopascals at station M2. The temperature of the air at M0 is 20 degrees Celsius. As the air is ascending, cloud formation sets in at 84.5 kilopascals. Consider a quantity of moist air ascending the mountain with a mass of 2,000 kilograms over each square meter. This moist air reaches the mountain ridge, station M2, after 1500 seconds. During that rise, an amount of 2.45 g of water per kilogram of air is precipitated as rain. Question 1. Determine temperature T1 at M1 where the cloud ceiling forms. Question 2. What is the height H1, at M1, above station M0 of the cloud ceiling assuming a linear decrease of atmospheric density? Question 3. What temperature T2 is measured at the ridge of the mountain range? Question 4. Determine the height of the water column, precipitation level, precipitated by the air, stream in 3 hours, assuming a homogeneous rainfall between points M1 and M2. Question 5. What temperature T3 is measured in the back of the mountain range at station M3? Discuss the state of the atmosphere at station M3 in comparison with that at station M0. Hints and data. The atmosphere is to be dealt with as an ideal gas. Influences of the water vapor on the specific heat capacity in the atmospheric density are to be neglected. The same applies to the temperature dependence of the specific latent heat of vaporization. The temperatures are to be determined to an accuracy of 1 Kelvin, the height of the cloud ceiling to an accuracy of 10 meters, and the precipitation level to an accuracy of 1 millimeter. Specific heat capacity of the atmosphere in the pertaining temperature range, Cp equals 1005 joule per kilogram per Kelvin. Atmospheric density for P0 and T0 at station M0 are ρ0 equals 1.189 kilograms per cubic meter. Specific latent heat of vaporization of the water within the volume of the cloud, Lv equals 2500 kilojoule per kilogram. Cp over Cv equals Chi equals 1.4 and G equals 9.81 meters per second square. Question 1. Determine temperature T1 at M1 where the cloud ceiling forms. Solution to question 1. Since the air moves adiabatically up the slope, we can apply Formula 1. Adiabatic dependence of temperature and pressure, which is converted to dependence 2 at points M0 and M1. The final answer is obtained from Formula 3. The temperature at point 1 of the cloud formation region is 279 Kelvin. This was the solution to question 1. Question 2. What is the height H1, at M1, above station M0 of the cloud ceiling assuming a linear decrease of atmospheric density? Solution to question 2. We believe that the density of the atmosphere depends linearly on the altitude. This means that the difference in pressure at points 0 and 1 is calculated based on the average value of the density of the atmosphere. That is, it is equal to ρ0 plus ρ1 divided by GH1. Formula 4. On the other hand, we have the formula for an ideal gas. Rho 0 by T0 divided by P0 is equal to Rho 1 by T1 divided by P1. Formula 5. From here we find Rho 1 from Formula 5. This density is equal to 1.070 kilograms per cubic meter. And using Formula 4, we get H1 is equal to 1,400 meters. This was the solution to question 2. Question 3. What temperature T2 is measured at the ridge of the mountain range? Solution to question 3. The temperature difference when the air is ascending from the cloud ceiling to the mountain ridge is caused by two processes, adiabatic cooling to temperature Tx and heating by delta T by condensation. As for the answer to question 1, we have formula 6, Tx equal 265 Kelvin. For each kilogram of air, the heat produced by condensation is LV multiplied by 2.45 gram, which is 6.125 kilojoule. From here we can find that delta T could be found from formula 7, which 6.1 Kelvin. Finally we have T2 equal 271 Kelvin. This was the solution to question 3. Question 4. Determine the height of the water column, precipitation level, precipitated by the air, stream in 3 hours, assuming a homogeneous rainfall between points M1 and M2. Solution to the fourth question. If 2.45 grams of water fell as rain from 1 kilogram of air in 1500 seconds, then from 2000 kilograms will fall 2.45 grams multiplied by 2000, which is 4.9 kilograms. And in 3 hours, 35.3 kilograms will fall on the surface of 1 square meter. Hence, the precipitation level will be equal to 35.3 kilograms divided by the density of 1000 kilograms per cubic meter and divided by the area of 1 square meter, which gives 0.035 meters or 35 millimeters. This was the solution to the fourth question. Question 5. What temperature T3 is measured in the back of the mountain range at station M3? Discuss the state of the atmosphere at station M3 in comparison with that at station M0. Solution to the question 5. Temperature T3 behind the mountain we can find from adiabatic heating to temperature T3, which is 300 Kelvin. The air has become warmer and drier. The temperature gain is caused by condensation of vapor. This was the solution to question 5. And here we finish discussion to problem 1. Problem 2. Electrons in a magnetic field. A beam of electrons emitted by a point source P enters the magnetic field vector B of a toroidal coil, toroid, in the direction of the lines of force. The angle of the aperture of the beam 2 by alpha 0 is assumed to be small, 2 by alpha 0 much less than 1. The injection of the electrons occurs on the mean radius r of the toroid with acceleration voltage v0. Neglect any interaction between the electrons. The magnitude of vector B, is assumed to be constant. Question 1. To guide the electron in the toroidal field, a homogeneous magnetic deflection field vector B1 is required. Calculate B1 for an electron moving on a circular orbit of radius r in the torus. Question 2. Determine the value of vector B which gives for focusing points separated by pi over 2 as indicated in the diagram. Note, when considering the electron paths you may disregard the curvature of the magnetic field. Question 3. The electron beam cannot stay in the toroid without a deflection field B1, but will leave it, with a systematic motion, drift, perpendicular to the plane of the toroid. Part A. Show that the radial deviation of the electrons from the injection radius is finite. Part B. Determine the direction of the drift velocity, Note, the angle of aperture of the electron beam can be neglected. Use the laws of conservation of energy and of angular momentum. Given data, charge E over mass m is 1.76 by 10 power 11 coulomb by kilogram, V0 equals 3 kilovolt, R equals 50 millimeters. Question 1. To guide the electron in a toroidal field, a homogeneous magnetic deflection field vector B1 is required. Calculate B1 for an electron moving on a circular orbit of radius r in the torus. Solution to the question 1, determination of B. The vector of the velocity of any electron is divided into components parallel with and perpendicular to the magnetic field B. Formula 1. The Lorentz force F equals negative E multiplied by cross product V. B influences only the perpendicular component. It acts as a radial force as in equation 2. Hence the radius of the circular path that has been traveled is in equation 3, and the period of rotation which is independent of V perpendicular is in formula 4. The parallel component of the velocity does not vary. Because of alpha 0 much less than 1, it is approximately equal for all electrons to V0. Expression 5, hence the distance B between the focusing points. Using equation 5, is in formula 6, B approximately equal V0T. From the law of conservation of energy follows the relation between the acceleration, voltage V0 and the velocity V0. Equation 7. Using equation 7 4 1 obtains from equation 6 B equal expression 8, and because of B equal 2 pi r over 4 1 obtains magnetic field B equal expression 9. That was solution to the question 1. Question 2. Determine the value of vector B which gives 4 focusing points separated by pi over 2 as indicated in the diagram. Note, when considering the electron paths you may disregard the curvature of the magnetic field.
Determination of B1. Analogous to equation 2 we have expression 10. From equation 7 follows magnetic field B1 equal to expression 11. That was solution for question 2.
Question 3. The electron beam cannot stay in the toroid without a deflection field B1, but will leave it, with a systematic motion, drift, perpendicular to the plane of the toroid. Part A. Show that the radial deviation of the electrons from the injection radius is finite. Question 3. Finiteness of R1 and direction of the drift velocity. In the magnetic field the lines of force are circles with their centers on the symmetry axis, z-axis of the toroid. In accordance with the symmetry of the problem, polar coordinates r and phi are introduced into the plane perpendicular to the z-axis, see figure below, and the occurring vector quantities, velocity, magnetic field B, Lorentz force, are divided into the corresponding components. Since the angle of aperture of the beam can be neglected, examine a single electron injected tangentially into the toroid with velocity v0 on radius big R. In a static magnetic field the kinetic energy is conserved, thus E equal 12. The radial points of inversion of the electron are defined by the condition V R equals 0. Using equation 12 one obtains expression 13. Such an inversion point is obviously given by small r equal vector big R in cylindric coordinates v phi equal v0, v r equals 0 and v z equals 0. To find further inversion points and thus the maximum radial deviation of the electron, the components of velocity v phi and v z in equation 13 have to be expressed by the radius. V phi will be determined by the law of conservation of angular momentum. The Lorentz force obviously has no component in the phi direction, parallel to the magnetic field. Therefore it cannot produce a torque around the z-axis. From this follows that the z component of the angular momentum is a constant, it means Lz equal mv phi small r equal mv0 big R and, therefore v phi equal v0 multiplied by big R over small r, equation 14. Vz will be determined from the equation of motion in the z direction. The z component of the Lorentz force is Fz equal negative E big B v R. Thus the acceleration in the z direction is Az equal expression 15. That means, since B is assumed to be constant, a change of Vz is related to a change of R as follows, delta Vz equal negative E over m by B delta R. Because of delta R equals small r minus big R and delta Vz equals Vz1 finds Vz equal expression 16. Using equations 14 and 15 from equation 13 we have dependency 17, where A equal E over m by B by big R over V0. Part B. Determine the direction of the drift velocity. Note, the angle of aperture of the electron beam can be neglected. Use the laws of conservation of energy and of angular momentum. Discussion of the curve of the right side of equation 17 gives the qualitative result shown in the following diagram. Hence R1 is finite. Since big R less or equal small r which is less 0. R equal R1 equation 16 yields Vz less than 0. Hence the drift is in the direction of the negative z-axis. Problem 3. Infinite LC grid. When sine waves propagate in an infinite LC grid, see the figure, the phase of the AC voltage across two successive capacitors differs by phi. Question A. Determine how phi depends on omega. L and C, omega is the angular frequency of the sine wave. Question B. Determine the velocity of propagation of the waves if the length of each unit is L. Question C. State under what conditions the propagation velocity of the waves is almost independent of omega. Determine the velocity. In this case, question D. Suggest a simple mechanical model which is an analog to the above circuit and derive equations which establish the validity of your model. Formulae: cosine alpha minus cosine beta equal negative 2 sine alpha plus beta over 2 multiplied by sine alpha minus beta over 2. Sine alpha minus sine beta equal 2 cosine alpha plus beta over 2 multiplied by sine alpha minus beta over 2. Question A. Determine how phi depends on omega. L and C, omega is the angular frequency of the sine wave. Solution for problem 3. Question A. According to Kirchhoff current law we have equations 1. According to Kirchhoff voltage law we have equations 2. Capacitive voltage drops is in equations 3. Note, in equations 3 is used I tilde instead of I because the current leads the voltage by 90 degrees. Inductive voltage drops is in equations 4. Note, in equations 4 is used I tilde instead of I because the current lags behind the voltage by 90 degrees. The voltage Vcn is given by formula 5. This formula follows from the problem. From equations 3 and 5 we have expression 6. From equations 4, 2, and using 5 we have expressions 7 and 8. Equations 6, 7 and 8 satisfy the current law. This gives the dependence of phi on omega, L and C. This condition must be true for any instant of time. Therefore it is possible to divide by V0 cosine omega t plus n phi. Hence omega square LC equal to 4 sin square phi over 2. And final result is 9. That was solution for question 1. Question B. Determine the velocity of propagation of the waves if the length of each unit is L. Solution of the second question. The signal transit time between adjacent capacitors is calculated by the phase difference phi divided by the angular frequency omega. So the distance L is covered in the time delta t, thus the propagation velocity is in expression 10. That was solution for question 2. Question C. State under what conditions the propagation velocity of the waves is almost independent of omega. Determine the velocity. In this case, solution of the question C. Slightly dependent means that this arcsine must be proportional to omega since speed v is constant in that case. This is true only for small values of omega. That means omega multiplied by square root from LC divided by 2 is much less than 1, and therefore V0 equal L over square root from LC. Expression 11. That was solution for question C. Question D. Suggest a simple mechanical model which is an analog to the above circuit and derive equations which establish the validity of your model. Solution for question D. The energy is conserved since only inductances and capacitances are involved. Using the terms of A, one obtains the capacitive energy in Formula 12 and the inductive energy in Formula 13. From this follows the standard form of the law of conservation of energy is Formula 14. The relation to mechanics is not recognizable in this way since two different physical quantities Vcn and Cin are involved and there is nothing that corresponds to the relation between the locus x and the velocity v as first derivative of x. To produce an analogy to mechanics, the energy has to be described in terms of the charge q, the current I as first derivative of q and the constants L and C. For this purpose the voltage Vcn has to be expressed in terms of the charges QLn passing through the coil. One obtains Formula 15. However, QLn could equally be another quantity, for example an angle. L could be for example a moment of inertia. From the structure of the problems follows, interaction only with the nearest neighbor, the force rises linearly with the distance. A possible model could be next one. That was solution for question D. And here we finish discussion for problem 3.